In the cathedral silence of deep space, where photons have journeyed through 13 billion years of cosmic night to whisper their ancient secrets into our telescopes, there exists a question so profound it threatens to unravel the very fabric of what we call reality. Time, that invisible current that sweeps our consciousness from birth toward death, that transforms potential into memory, that gives meaning to every heartbeat and every dying star. Maybe nothing more than a local accident, a temporary arrangement of existence that governs only our small corner of an infinitely stranger universe. Right now, in this suspended moment, time moves forward with absolute certainty. Atomic clocks tick with mechanical precision. Radioactive elements decay according to immutable half-lives. The cosmic microwave background grows colder as space itself expands, carrying the universe inexorably from its fiery birth toward its ultimate fate. This arrow of time seems as fundamental as gravity, as unchanging as the speed of light. Yet what if this temporal river that defines human experience, this progression from cause to effect, from question to answer, from hope to fulfillment, is merely an illusion, a local weather pattern in the vast climate of existence? Beyond the edge of observable space, in dimensions our instruments cannot penetrate, in parallel realities that may exist layered above and below our own like pages in an infinite book, time itself might behave according to laws so alien that our entire conception of sequence, causality, and duration becomes as meaningless as asking which direction is north in the weightless void between galaxies. This possibility haunts the equations of modern physics like a persistent shadow. From the laboratories buried miles beneath mountains where particle accelerators probe the quantum foam, to the observatories perched on remote peaks where scientists peer into cosmic abysses older than Earth itself, evidence accumulates, subtle, indirect, but undeniable, that our temporal experience may be as limited and provincial as a mayfly's understanding of seasons. The mathematics that describe black holes suggest regions where time stops entirely. Quantum mechanics reveals particles that seem to communicate instantaneously across vast distances, as if temporal separation were merely a human misconception. Cosmological models predict parallel universes where time might flow backward, branch into multiple streams, or exist in dimensions we cannot even imagine. If these theories prove correct, then consciousness itself, this fleeting pattern of awareness that depends utterly on time's forward flow, exists within a bubble of temporal order floating in an ocean of chronological chaos. The implications stretch beyond science into the deepest questions of meaning, identity, and existence itself. Discovery phase. Einstein's temporal revolution, the transformation of humanity's understanding of time, began not with cosmic observations or quantum experiments, but with a single, deceptively simple question posed by a young patent clerk in Bern, Switzerland. Albert Einstein, surrounded by the mundane mechanics of invention applications and clockwork mechanisms, found his mind wandering toward a mystery far more profound than any device crossing his desk. In the quiet hours of 1905, as the Swiss countryside settled into evening beyond his office windows, Einstein contemplated the nature of simultaneity itself, and in doing so, opened a doorway into the deepest mysteries of temporal reality. The question that consumed him seemed almost childlike in its simplicity. What does it truly mean for two events to happen at the same time? For centuries, humanity had assumed the answer was obvious. Time flowed uniformly throughout the universe like an invisible river, carrying all events in its current. Newton's clockwork cosmos ticked with absolute precision, its temporal machinery governing everything from falling apples to orbiting planets with mathematical certainty. Time was time, everywhere and always, the universal stage upon which the drama of physics unfolded. But Einstein's intuition whispered of something far stranger. Through his famous thought experiments, trains racing past platforms while lightning strikes illuminate the night, observers moving at different speeds, watching the same events unfold. He he began to glimpse the shocking truth. Time was not absolute. It was relative, malleable, dependent on the observer's motion through space. What seemed simultaneous to a passenger on a speeding train occurred at different moments for someone standing on the platform. The faster you moved, the more dramatically time dilated, stretching like taffy pulled by invisible hands. The mathematical framework of special relativity that emerged from these insights revealed time as the fourth dimension of space-time itself, inseparably woven with the three dimensions of space into a fabric that could bend, stretch, and curve. But Einstein's revelation reached far deeper than anyone initially comprehended. If time could be dilated by motion, if simultaneity was merely a matter of perspective, then time itself was not the unchanging backdrop of existence. It was part of the performance. The confirmation of Einstein's theories came gradually, through observations that seemed to violate common sense. Atomic clocks carried on high-speed aircraft ran slower than identical clocks left on the ground. Particles accelerated to near-light speeds and laboratories lived longer than their stationary counterparts, as if time itself granted them extended lifespans. GPS satellites required constant temporal corrections to maintain accuracy, their onboard clocks running fast in the weaker gravitational field of orbit. Each experiment confirmed the same impossible truth. Time was not universal but local, not absolute but relative, not fixed but fluid. Einstein later extended these insights through general relativity, revealing that massive objects warp the very geometry of space-time, creating gravitational wells where time passes more slowly. Near the surface of a neutron star, where gravity approaches the theoretical maximum possible in stable matter, time crawls at a pace that would seem frozen to distant observers. At the event horizon of a black hole, time dilation becomes so extreme that external observers would see infalling matter appear to stop completely, forever suspended at the edge of the unknowable. Yet even Einstein could not have foreseen the ultimate implications of his discoveries. His equations didn't merely describe flexible time. They hinted at something far more radical. The mathematics suggested that time might be emergent rather than fundamental, that at the deepest levels of reality, temporal flow might dissolve entirely into more basic processes. The framework he created opened pathways toward understanding dimensions where causality becomes meaningless, where the concepts of before and after break down completely, where the arrow of time that defines human experience might be as local and limited as the particular pattern of weather occurring outside a single window. In those early decades of the 20th century, as Einstein grappled with the implications of his own theories, he unknowingly began humanity's journey toward the recognition that our temporal experience, our flowing sense of past, present, and future, might be nothing more than one possible arrangement among infinite others. The revolution had begun, but its destination remained shrouded in mystery, pointing toward questions about the nature of time that would haunt physics for generations to come. Scientific shock, the block universe revelation, the mathematical consequences of Einstein's relativity led to a conclusion so profoundly disturbing that many physicists, including Einstein himself, initially recoiled from its implications. If the equations were correct, if space and time truly formed an inseparable four-dimensional fabric, then the flowing river of time that defines human consciousness was nothing more than an elaborate illusion. Past, present, and future existed simultaneously in what came to be known as the block universe, a static four-dimensional structure where every moment that ever was or ever would be coexisted in eternal, unchanging reality. Hermann Minkowski, Einstein's former mathematics professor, was the first to fully grasp the revolutionary implications of his students' work. In 1908, Minkowski presented a paper that would forever alter humanity's conception of temporal reality. Henceforth, he declared with characteristic precision, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski had discovered in Einstein's equations was not merely a new physics, but a new metaphysics, a description of reality where time was revealed to be as static and unchanging as space itself. In Minkowski's space-time, the universe resembled a vast, four-dimensional sculpture where every event, from the birth of stars to the flutter of a butterfly's wing, existed as a permanent feature carved into the structure of reality. Your first breath and your final heartbeat occupied specific coordinates in this block, as fixed and eternal as the position of a mountain peak on Earth's surface. The sensation of moving from past to future, the feeling that the present moment held some special significance, became analogous to driving through a landscape and mistaking the changing view for motion in the terrain itself. The implications were staggering and deeply unsettling. If the block universe accurately described reality, then free will become questionable. How could choices be free if the outcomes already existed somewhere in the four-dimensional structure? Death lost its finality. Every moment of life existed permanently in the block, making mortality a change in perspective rather than an ending. The very notion of becoming, of potential transforming into actuality, dissolved into the static geometry of space-time. But the block universe revelation raised an even more profound question that would echo through the corridors of physics for decades to come. If time didn't truly flow within our reality, if our four-dimensional universe was indeed a static structure where all moments coexisted, then what temporal architecture might characterize the broader reality from which our universe emerged? If consciousness created the illusion of temporal flow within a changeless block, then in dimensions beyond our perception, where consciousness might not exist or might exist in radically different forms, what incomprehensible temporal structures might govern existence? The block universe suggested that our experience of duration, of change, of the poignant passage from youth to age, might be as limited and provincial as a two-dimensional being's understanding of depth. Just as we struggle to visualize four-dimensional geometry, we might be fundamentally incapable of comprehending the true temporal structure of reality itself. Our flowing time might be analogous to a shadow cast by higher-dimensional temporal processes too complex for human minds to grasp. Some physicists attempted to preserve the reality of temporal flow through various interpretations, but the mathematics remained implacable. The block universe wasn't merely one possible model. It was the direct consequence of treating Einstein's theory seriously. If relativity was correct, and decades of precise experimentation suggested it was, then the flowing time of human experience was revealed as a persistent illusion, a trick of consciousness that made navigation through the four-dimensional block possible but mistook the map for the territory. The revelation sent shockwaves through philosophy and science alike. If consciousness was responsible for creating the illusion of temporal flow within a static reality, then outside our bubble of awareness, in parallel universes, in higher dimensions, in the substrate from which space-time itself emerged, time might operate according to principles so alien to human experience that our entire vocabulary of causation, sequence, and duration would become meaningless. The block universe was not merely a new model of time. It was a window into the possibility that our temporal experience represented only one note in an infinite symphony of temporal possibilities, most of which remained forever beyond the reach of human comprehension. Deeper investigation, quantum mechanics, and temporal uncertainty as the 20th century progressed beyond Einstein's revelations. A new revolution in physics emerged from the laboratories where scientists probed matter's smallest scales. Quantum mechanics, with its strange mathematics of probability and uncertainty, introduced temporal mysteries that seemed to challenge even the block universe model. In the quantum realm, particles existed in ghostly superpositions of multiple states until observed, suggesting that the future might remain fundamentally open, uncertain, undefined until consciousness collapsed infinite possibilities in a singular reality. The phenomenon revealed itself first through the double-slit experiment, that deceptively simple demonstration that would become quantum mechanics' most haunting mystery. Individual particles, photons, electrons, even complex molecules, when fired toward two parallel slits, somehow passed through both simultaneously, creating interference patterns impossible unless each particle traveled all possible paths at once. But the moment any measurement attempted to determine which slit the particle used, the superposition collapsed into a single, definite trajectory. Reality seemed to crystallize from quantum foam only when observed, suggesting that time's arrow might emerge from the interaction between consciousness and quantum possibility. But quantum mechanics held deeper temporal secrets. John Wheeler, the physicist who coined the term black hole, devised experiments that pushed the boundaries of causality itself. His delayed choice quantum eraser experiment demonstrated that decisions made in the present could apparently determine the past states of quantum systems. Photons seemed to decide their history retroactively, based on measurements that occurred after they had already interacted with detectors. The arrow of time, so fundamental to human experience, became blurred at quantum scales where past and future seemed to negotiate their relationship through mysterious quantum correlations. Even stranger was the phenomenon of quantum entanglement, Einstein's spooky action at a distance. When particles became entangled, measuring the state of one instantaneously determined the state of its partner, regardless of the spatial distance separating them. The correlation transcended space in ways that seemed to violate the cosmic speed limit imposed by light. But subsequent research suggested something even more unsettling. Entangled particles might also transcend temporal separation. Experiments in quantum retrocausality, pioneered by researchers like Yakir Aharonov and Avshalom Elitzur, revealed evidence that quantum effects might propagate backward through time itself. Future measurements appear to influence the outcomes of past experiments, creating temporal loops where cause and effect became indistinguishable. If these results were valid, then at the quantum level, the foundation upon which all matter and energy are built, the arrow of time became meaningless. Past and future engaged in bidirectional communication through quantum channels that operated outside the constraints of classical causality. The implications reached far beyond laboratory curiosities. If quantum mechanics governed the fundamental structure of reality, and if quantum mechanics treated time as reversible and uncertain, then what did this suggest about temporal flow and dimensions where quantum effects might dominate completely? Could there exist realms where quantum retrocausality was the norm rather than the exception, where futures routinely determined pasts in endless temporal loops, where linear progression from cause to effect became impossible? The measurement problem in quantum mechanics added another layer of temporal mystery. The mathematics suggested that quantum superpositions should persist indefinitely, with particles existing in all possible states simultaneously. Yet macroscopic objects seem to inhabit definite states, following classical physics where time moved decisively forward. Somewhere between the quantum and classical scales, superposition collapsed into certainty, probability transformed into fact, and the multiple potential timelines of quantum possibility narrowed into the single timeline of human experience. Various interpretations of quantum mechanics offered different solutions to this temporal puzzle. The Copenhagen interpretation suggested that measurement itself collapsed superposition, making consciousness a participant in determining reality structure. The many worlds interpretation proposed that all quantum possibilities were equally real, existing in parallel timelines that branched at every quantum event. If true, then outside any single timeline, in the space between worlds, time might flow in all directions simultaneously, creating metatemporal structures where every possible history coexisted in quantum superposition. The quantum revolution revealed that even the sophisticated block universe model might be incomplete. If reality's foundation operated according to quantum principles where time was bidirectional and uncertain, then the static four-dimensional block might itself be embedded in higher-dimensional temporal structures where causality, sequence, and duration obeyed laws completely alien to human intuition. The deeper physics probed into matter's heart, the more mysterious time became, and the more our local experience of temporal flow appeared to be just one temporary arrangement in an infinite space of temporal possibilities. Escalation, cosmic mysteries, and temporal anomalies as humanity's observational capabilities expanded throughout the late 20th and early 21st centuries. Astronomers began mapping the cosmos with unprecedented precision, revealing phenomena that challenged the assumption of temporal uniformity across the universe. The cosmic microwave background radiation, that ancient light from the universe's infancy, stretched by 13 billion years of cosmic expansion, carried patterns that suggested space-time itself might not age uniformly. Some regions of the universe appeared to experience time differently than others, as if the cosmos were a vast patchwork of temporal domains operating according to subtly different chronological laws. The discovery of dark energy presented an even more profound challenge to temporal consistency. This mysterious force, comprising 70% of the universe's total content, yet remaining completely invisible and undetectable except through its gravitational effects, was driving space itself to expand at an accelerating rate. The implications for time were staggering. As dark energy stretched space-time exponentially, distant regions of the cosmos were racing away from us at velocities approaching the speed of light, creating relativistic effects so extreme that their temporal reference frames were becoming fundamentally disconnected from our own. In the far reaches of space, where dark energy's influence dominated over gravity's attractive pull, time itself was beginning to flow differently. Galaxy clusters separated by billions of light years were experiencing temporal dilation effects that meant their now was increasingly out of synchronization with Earth's present moment. The universe was not aging uniformly. It was developing temporal gradients, regions where time passed at different rates, creating a cosmic landscape where simultaneity became a purely local concept. But the most extreme temporal anomalies existed within our own cosmic neighborhood, in the form of black holes. Those gravitational monsters where Einstein's equations predicted that space-time curvature became infinite. At a black hole's event horizon, time dilation reached theoretical extremes that defied human comprehension. From the perspective of a distant observer, matter falling toward the black hole would appear to slow down progressively, its light stretching toward longer, redder wavelengths until it became effectively frozen at the horizon, suspended forever in a moment that never quite arrived. Yet from the perspective of the infalling observer, time continued normally until reaching the singularity at the black hole's center, a point where the mathematics of general relativity broke down completely and space-time itself became undefined. The singularity represented a boundary beyond which the concept of time lost all meaning, with a temporal structure that governed the rest of the universe simply ceased to exist. Stephen Hawking's groundbreaking work on black hole thermodynamics revealed even stranger temporal properties. Black holes possess temperature and entropy, thermodynamic properties that suggested they were not completely isolated from the rest of the universe. Through quantum effects near the event horizon, black holes slowly evaporated, emitting Hawking radiation that carried energy away from the gravitational well. But this radiation appeared to contain no information about the matter that had fallen into the black hole, creating the information paradox, a fundamental conflict between quantum mechanics and general relativity that suggested our understanding of time and causality was incomplete. The holographic principle, developed to resolve this paradox, proposed that all information within a black hole's volume was actually encoded on its two-dimensional surface. If true, then the three-dimensional reality we experienced, along with its temporal structure, might be emergent from lower-dimensional processes that operated according to completely different temporal principles. Our flowing time might be analogous to the images on a television screen, apparently three-dimensional, but actually projected from two-dimensional information sources operating outside the spatial and temporal framework we perceived as reality. Cosmic inflation theory added another layer of temporal complexity to the picture. The hypothesis suggested that our observable universe was just one bubble in an infinite multiverse, where different regions underwent inflation at different times and rates. Some bubbles might still be inflating exponentially, their internal time stretched to such extremes that billions of years passed in what external observers would perceive as moments. Other bubbles might have completed inflation eons ago, their internal temporal evolution proceeding at rates completely disconnected from our cosmic chronology. These discoveries painted a picture of a universe far stranger than the uniform temporal landscape that human intuition expected. Our local experience of synchronized time, where cause reliably preceded effect and duration remained consistent, appear to be extraordinarily rare in the cosmic context. Most of the universe existed in states where temporal relationships became arbitrary, where simultaneity lost meaning, where the very concepts of before and after dissolved into relativistic ambiguity. We inhabited a small island of temporal order floating in an ocean of chronological chaos. And the more precisely we mapped the cosmos, the more isolated our temporal experience appeared to be. Theories and speculations, models of nonlinear time, the accumulating evidence that time might not be universal, that our temporal experience might be just one local manifestation of deeper, more complex temporal structures, has driven theoretical physicists to develop increasingly sophisticated models of how time might operate outside our reality. These theories, while speculative, are grounded in rigorous mathematics and represent humanity's most ambitious attempts to comprehend temporal possibilities that transcend human experience. String theory, the most mathematically elegant attempt to unify quantum mechanics with general relativity, requires additional dimensions beyond the four we experience directly. In the standard model of string theory, reality possesses 11 dimensions, 7 more than the length, width, height, and time that define our perceptual world. But these extra dimensions are not merely spatial. Some theoretical frameworks suggest they might include additional temporal dimensions, creating a multidimensional temporal landscape where time itself has multiple directions and degrees of freedom. Brian Greene and other leading string theorists have proposed that our three-dimensional space and one-dimensional time might be confined to what they call a brane, a lower-dimensional surface floating in a higher-dimensional bulk space where temporal relationships operate according to completely alien geometries. From this perspective, our flowing time would be analogous to shadows cast by higher-dimensional temporal structures too complex for human consciousness to perceive directly. The linear progression from past to future that defines our experience might be just one cross-section through a multidimensional temporal manifold where causality operates according to principles we cannot even conceptualize. Loop quantum gravity offers an even more radical reconceptualization of time's nature. This approach to quantum gravity proposes that space-time itself is quantized at the smallest possible scales, composed of discrete units that exist below the Planck length and Planck time, scales so tiny that the very concepts of continuous space and flowing time break down into quantum granularity. In this model, time becomes granular rather than continuous, advancing through discrete quantum jumps between moments that exist as fundamental units of temporal reality. If loop quantum gravity accurately describes space-time's foundation, then at scales smaller than human perception can reach, time might stutter and skip like a cosmic film projector, with each frame representing a discrete moment in the quantum evolution of reality. Outside our macroscopic experience, where quantum effects dominate over classical physics, time might fragment into quantum superpositions of multiple simultaneous moments, creating temporal landscapes where linear progression becomes impossible to define. The many-worlds interpretation of quantum mechanics suggests perhaps the most mind-bending possibility of all, that every quantum measurement splits reality into multiple parallel timelines, each representing a different possible outcome of the quantum event. In this model, consciousness experiences only one timeline among infinite others, but all possible histories coexist in a vast multiverse of parallel realities. Outside any individual timeline, in the space between worlds, time might flow in all directions simultaneously, creating metatemporal structures where every possible sequence of cause and effect exists as an equally valid reality. Hugh Everett III, who first proposed the many-worlds interpretation, envisioned a universal wave function that encompasses all possible quantum states and their temporal evolution. From this perspective, our experience of linear time would be just one path through an infinite branching structure where all potential futures and past coexist. The arrow of time that gives meaning to human experience would be revealed as an artifact of consciousness navigating through one particular branch of an infinitely ramifying temporal tree. Eternal inflation theory extends these concepts to cosmological scales, proposing that our universe is just one bubble in an infinite multiverse where different regions undergo inflation at different rates and times. Some bubbles might experience reverse causality as their natural temporal direction, with effects preceding causes in their internal chronology. Others might have circular time, where temporal sequences loop back on themselves endlessly, making the concepts of beginning and ending meaningless. Still others might exist in temporal dimensions orthogonal to our own, where time flows in directions that our consciousness cannot even imagine. Alan Guth and Andre Linde, the architects of inflation theory, have calculated that in the broader multiverse, regions with our particular temporal structure, where causality flows reliably from past to future, might be extraordinarily rare. Most of reality might exist in states where temporal relationships become arbitrary, where the arrow of time points in random directions, where consciousness as we understand it could not exist because the temporal framework necessary for memory and anticipation would be absent. Perhaps the most radical possibility emerges from the holographic principle, developed to resolve paradoxes in black hole physics. This principle suggests that our four-dimensional space-time reality might be entirely emergent from information processing occurring on a lower dimensional boundary, where time might not exist at all. If consciousness and temporal experience are patterns that arise from timeless information processing, then the substrate of reality itself, the foundation from which our temporal experience emerges, might be completely atemporal. From this perspective, all temporal structures, linear time, circular time, branching time, multidimensional time, might be equally valid patterns that can emerge from more fundamental, timeless processes. Our flowing time would be analogous to music arising from the silent vibration of piano strings, existing only as a pattern of organization that emerges temporarily from deeper, changeless foundations. The possibility suggests that outside our reality, in the timeless substrate from which all temporal experience emerges, existence itself might transcend the very categories of temporal and atemporal, creating possibilities for being that consciousness confined to linear time cannot even begin to comprehend. Scientific tools and ongoing testing, probing reality's temporal boundaries, the speculative theories about time's nature outside our reality are gradually transitioning from pure mathematics to testable hypotheses as scientific instruments reach unprecedented levels of precision and sensitivity. Across the globe, in underground laboratories, orbital observatories, and theoretical physics institutes, researchers are developing increasingly sophisticated tools to probe the deepest questions about temporal reality structure. Deep beneath the French-Swiss border, the Large Hadron Collider at CERN accelerates protons to energies approaching those that existed moments after the Big Bang, searching for evidence of extra dimensions where time might behave according to different laws. The collisions between these high-energy particles create conditions so extreme that they might momentarily tear holes in space-time itself, allowing glimpses of higher-dimensional temporal structures. Theoretical calculations suggest that if additional time dimensions exist, they would leave subtle signatures in the particle debris produced by these cosmic-scale collisions, patterns that could reveal whether our linear time is embedded in a larger temporal manifold. The recent upgrades to the LHC have pushed energy levels to unprecedented heights, enabling searches for particles that might exist partially outside our temporal framework. Kaluza-Klein gravitons, hypothetical particles that could travel through extra dimensions, would appear in our reality with characteristics that depend on the temporal structure of the higher dimensional space they traverse. If discovered, these particles would provide the first direct evidence that time operates differently outside the four-dimensional space-time we inhabit. Gravitational wave detectors represent another frontier in temporal research. The LIGO and Virgo interferometers, sensitive enough to detect space-time distortions smaller than 1,000th the width of a proton, have opened an entirely new window into the universe's temporal architecture. When black holes merge or neutron stars collide, they create ripples in space-time itself that carry information about the extreme temporal conditions near these cosmic monsters. Advanced analysis of gravitational wave data is revealing how time behaves in the universe's most extreme environments, where general relativity's predictions approach their theoretical limits. Future space-based gravitational wave detectors, such as the proposed laser interferometer space antenna, will extend this sensitivity to even more exotic phenomena. These instruments might detect gravitational waves from cosmic strings, hypothetical one-dimensional defects in space-time that could stretch across the universe. If cosmic strings exist, they would create unique gravitational signatures that depend on their temporal properties, potentially revealing whether time flows differently along these cosmic fault lines. The James Webb Space Telescope and next-generation cosmic microwave background missions are mapping the universe's earliest moments with precision that approaches the theoretical limits imposed by quantum mechanics. These observations are searching for temporal anomalies in the cosmic microwave background, patterns that might indicate regions where time flowed differently during the universe's infancy. Subtle temperature variations in this ancient radiation could reveal evidence of parallel universes with different temporal structures, cosmic inflation events that occurred at different rates, or even signatures of pre-Big Bang physics, where time might have operated according to completely different principles. Quantum computing research has opened unexpected avenues for investigating time's nature at the microscopic scale. Quantum computers operate by manipulating quantum superpositions, states where particles exist in multiple conditions simultaneously, in ways that seem to transcend classical temporal limitations. Recent experiments have demonstrated quantum algorithms that appear to process information from multiple timelines in parallel, suggesting that quantum computers might provide glimpses of how computation and information processing could work in realms where linear time doesn't apply. The field of quantum retrocausality is developing increasingly sophisticated experiments to test whether quantum effects can genuinely propagate backward through time. Researchers at universities worldwide are conducting delayed choice experiments with quantum systems that seem to challenge our understanding of temporal causality. These experiments use quantum entanglement to create situations where measurements made in the present appear to influence the past states of quantum systems, suggesting that at microscopic scales, the arrow of time might be more flexible than classical physics predicts. Theoretical physicists are also developing mathematical frameworks to describe how consciousness might emerge from timeless quantum processes. These models attempt to explain how subjective temporal experience, the flowing sense of past, present, and future, could arise from objective quantum mechanics, where time appears to be reversible and uncertain. If successful, these theories could provide testable predictions about how time would appear to observers existing partially outside our reality's temporal framework. The search for evidence of parallel universes, extra dimensions, and nonlinear temporal structures has become one of the most active frontiers in modern physics. While direct detection remains challenging, indirect evidence continues to accumulate through cosmic ray observations, particle physics experiments, and precision tests of general relativity in extreme gravitational fields. Each new measurement pushes the boundaries of our understanding, gradually revealing whether our temporal experience is universal or merely one local arrangement in an infinite space of temporal possibilities. The tools now being developed might soon provide definitive answers to questions that have haunted physics for decades. Within the next generation, humanity might discover whether time truly flows differently outside our reality, or whether our flowing temporal experience is as universal and fundamental as we have always believed it to be. Philosophical reflection and emotional close. The meaning of temporal existence in the vast cathedral of cosmic time, where light from distant galaxies carries whispers of events that occurred before Earth existed, humanity finds itself confronting a possibility both beautiful and terrifying. That our experience of temporal flow, this progression from birth to death, from question to understanding, from hope to memory, might be nothing more than a local accident, a temporary arrangement of consciousness floating in an ocean of unimaginable temporal complexity. If the theories explored by modern physics prove correct, if time truly flows differently outside our reality, then the very foundations of human meaning must be reconsidered. The linear progression that gives structure to life, childhood flowing into adulthood, effort leading to achievement, love deepening through shared duration, would be revealed as one possible arrangement among infinite others. In realms where time moves backward, where cause and effect blur into quantum superposition, where consciousness might experience all moments simultaneously, the concepts that give human existence its poignancy and purpose might dissolve into mathematical abstractions. Yet perhaps this apparent limitation contains its own profound truth. If our flowing time is indeed rare in the broader cosmos, if consciousness requires this particular temporal structure to exist, then awareness itself becomes precious beyond measure. Every heartbeat, every thought, every moment of connection between conscious beings represents something extraordinary, not because it is eternal, but because it is so improbable. In a universe where most of reality might exist in timeless states or chaotic temporal loops, the emergence of consciousness capable of experiencing linear time becomes a miracle of cosmic rarity. The possibility transforms death from an ending into a transition between temporal states. If multiple time dimensions exist, if parallel universes branch from every quantum event, if our memories and experiences are encoded in the holographic structure of space-time itself, then the cessation of biological processes might not represent true termination, but rather a change in temporal perspective. The patterns of information that constitute consciousness might persist in forms that transcend our current understanding of temporal existence, continuing their evolution according to principles we cannot yet comprehend. But the deepest implication concerns the nature of meaning itself. Human beings find purpose through temporal relationships, through the possibility that present actions might influence future outcomes, that suffering might lead to wisdom, that love might endure beyond individual lifetimes. If time flows differently outside our reality, if causality becomes arbitrary in higher dimensions, then the ethical frameworks that guide human behavior might need fundamental reconceptualization. Perhaps meaning emerges precisely from temporal limitation. The poignancy of human experience might depend on the arrow of time that makes loss possible, that transforms potential into memory, that gives weight to choices by making them irreversible. In realms where all possibilities coexist simultaneously, where past and future merge into eternal present, the dramatic tension that makes life meaningful might be absent. Our temporal bubble might be where the universe develops not just consciousness, but the capacity for hope, regret, love, and transformation, experiences that require the flowing time we often take for granted. The scientific quest to understand time's nature outside our reality becomes, ultimately, an exploration of what it means to be human in a cosmos far stranger than our ancestors ever imagined. We are temporal beings contemplating eternity, local observers trying to comprehend the global nature of time itself, finite minds reaching toward infinite possibilities. The very act of asking these questions, of using our brief moment of conscious existence to probe the deepest mysteries of temporal reality, might be the universe's way of coming to know itself. In the end, whether time flows uniformly throughout all reality or operates according to alien principles and dimensions beyond our perception, The fact that consciousness exists to contemplate these possibilities remains extraordinary. We are patterns of information organized in such precise ways that space-time itself becomes aware of its own structure. Our questions about time's nature represent the cosmos asking questions about itself. Using the temporary arrangements of matter and energy, we call human beings as instruments of cosmic self-discovery. The mystery endures, suspended like a question mark written in the geometry of space-time itself. In laboratories around the world, telescopes peer deeper into cosmic time, while particle accelerators probe the quantum foundations where temporal causality begins to blur. The answer, whether our flowing time is universal or merely local, whether consciousness exists throughout the cosmos or only in rare pockets of temporal order, remains tantalizingly beyond our grasp. But perhaps the meaning lies not in solving the mystery, but in our capacity to contemplate it, to stand at the edge of known physics and peer into the temporal abyss, wondering what forms of existence might emerge from structures of time so alien that consciousness itself would need to be reimagined to comprehend them. We are temporal beings contemplating eternity, local observers trying to understand the global nature of time itself, finite minds reaching toward infinite possibilities. In this moment, this fleeting arrangement of matter and consciousness that experiences itself as now, we carry the universe's curiosity about its own temporal nature. Whether that curiosity extends beyond our reality, whether consciousness exists in realms where time flows backward or branches into infinite streams, whether awareness itself transcends the temporal limitations that seem to define it, remains one of existence's deepest questions. The cosmos keeps its temporal secrets well. But in the very act of asking, in the persistence of wonder that drives us to probe these ultimate mysteries, something profound persists, a pattern of questioning that might itself transcend the local arrangements of time and space that gave it birth. In seeking to understand whether time flows differently outside our reality, we participate in something larger than ourselves, the universe's eternal quest to comprehend its own infinite nature.